Hello and welcome back to the lab. Today on the bench we have one of the more interesting plugins in the 7000 series. We have a 7A13. This is a differential comparator and it has a bandwidth of about 100 megahertz depending on which frame you put it in. There's another plugin, a very similar plugin in the 7A22. However, there are some notable differences between the 7A22 and the 7A13. So having both is always good. 7A13 is 100 megahertz, 7A22 is 1 megahertz, but this goes down to 1 millivolt per division at its lowest range. This goes down to 10 microvolts per division at its lowest range. So both of these two units, one of their claims to fame is they have a amazingly good common mode rejection ratio, CMMR, and the 7A22 is actually duplicate functionality. So these two are almost the same. This is just the TM500 unit. This is the 7000 series unit. So almost identical plugins on these two specification-wise. So because both of these plugins are differential, wonderful common mode rejection ratio, we're going to take on the 7A13 today. One of the really nice things about this is it has a DC offset that is calibrated and fairly accurate for the time on this one, so we will get into that. But as with everything, starting the alignment process or restoration process, we're going to crack this open, we're going to service all the switches, all the cams, get everything all back to rights, and then we'll see if there's any problems from there. Here's a good look inside one of these plugins. I just took the right-hand side cover off. Some of the problems to be aware of in this particular unit are these micro relays. When these things start having problems, they can be challenging at best to source and bordering on unobtainium. There's two versions of the 7A15 or the 7A13. One has a mechanical section up in here, and it uses plastic gears in that mechanical section. That does not age well. So if you can get the digital version, that is definitely preferred. So we have two pots here that I need to clean. We have a cam switch that will service. I do not know what these ICs do yet. Oh, this one's gonna be fun to adjust. I gotta get that one added from the bottom. To get full bandwidth out of this, I'm gonna have to do the alignment in my 7904. So, this one comes to us by Ford's Sterling Engine division. Here's the other side. We have a couple more micro relays, lots of shielding up in this area, which is to be expected given how sensitive this input is. We have some pin throughs. These are notorious problem connections with cracked solder joints. Nice looking diode here. Interesting the way they've done the input on these. They have a leg. They're four-leg devices, but it's not sure if those are FETs or if those are probably FETs, and they come off to the two different inputs on the can. The interesting thing about these are this clamp that they have around the transistors. This thermally bonds them together so that they both stay at the same temperature. A lot of tech gear does that. Oh, wow, there's even more of those micro relays buried in here. Way down under here. This is a pretty complex mechanical design, actually, on this one. Well, I was doing the inspections, and there is a lot of custom controls on this particular unit. This potentiometer with a hole in the back of it. We've got this switch with a whole mechanical armature to make this work correctly. I got this potentiometer with a switch mounted to the back of it, so if any of these controls go sideways, replacement's going to be iffy. There's a lot of mechanical that was done for this one to make this plug-in work correctly and get it up and running. A couple of these couplers, these are known to crack. This one's no big deal. This one is not used often. It's a more rare coupler, and a lot of this front end stuff over here, if any of this goes south, then just due to age and the plastics getting brittle and things like that, then this is going to be really, really hard to get back up and running. So take that into consideration before jumping on one of these. They're nice plugins, but they do have both of them, the new and the old, have their issues. I was hoping I wasn't going to have to dig too much on this one for restorations. However, I don't know how well the camera's picking this up, but right here, that is some corrosion, and this lead on this electrolytic capacitor is very oxidized. So we are going to swap these two caps, and there's one other cap on the other side that we're going to pull out and swap as well. Other than that, there is not many ceramic caps in here. So, but as the soldering iron warms up, I'm going to clean this edge connector back here. So we have our two capacitors replaced. I did not have a 10 microfarad at 50 volts in the lab, but these 22s at 50 volts will work just fine in this position. The board was not damaged. We caught the corrosion just in time, so even though we were spilling electrolyte, everything's good and don't have to go any further, which is fantastic. I would not want to have had to extract this board out of this plug-in. So at this point, I'm ready for a power up. Everything's serviced. These two caps were replaced. Actually, I think I want to replace, since I got all the irons on and everything, I think I want to replace. I want to look and see what that guy does. And I'm also going to look at this guy over here. So I may want to replace these two as well. Okay, I've gotten the capacitors replaced. We have this one and these two. And these two, and I did confirm on the data sheet that these are all electrolytics. So we're ready for our first power up. So we'll pull this out just in case something exciting happens. I don't expect it to, but we'll see what happens. $100 millivolts, 0.1 volts, so readout's working. The voltage is working because the display's changing. Full bandwidth, everything looks good. Let's see if I can bring it. Yep, I can bring a trace up. Dim that out so we don't torture the tube. All right, let me throw this 7A26 in. I'm going to toss some signal on this comparator. Just make sure it stays triggering for a while. Doesn't have any warm-up faults before we get into a alignment on it, because like what happened with the 475, and one of the reasons why that took so long is there were some oddball intermittent faults on it that only showed up when it was warm. So I have the negative input grounded. I have the positive input set to DC, so this is going to work just like a regular scope plug-in. And we'll throw some signal on it function generator. We'll fire up the FG502 and we'll throw some triangle waves on it and see what happens. Okay, we have some nice stable triangle waves. Everything looks good. I'm just going to let this run for now. I'm going to back the screen off and the readout off so I don't torture the tube, and we're just going to let it sit. I'm going to monitor it with the triggered light, so if the triggered light goes out, something went wrong, but as long as the triggered light doesn't go out, it'll be fine. I'll let this run. If it runs for a while, gets nice and warm, doesn't have a problem, doesn't let off the magic smoke, we'll get into an alignment. Okay, I am setting up the 7A13. Everything's been through a warm-up period, and my 7510 is going to be okay here in a minute. So we're going to get started on the 7A13. This is such a sensitive plug-in that I'm going to rotate this real quick. You can actually see the thermal lag a little bit in the transistors for this plug-in. So that's why some of these controls are in the front, like the step attenuation balance, the 10x balance, and the variable balance. All of this is in the front. Typically, I would do these in a scope as I was going through the alignment procedure. However, for this particular plug-in, these need to be adjusted. There is 4 adjustments: the variable balance, the step attenuator balance, the 10x balance, and the gain adjustment that need to be done every time you move this to a different scope. It's affected by the power supplies in the frame, how well they're in tolerance with each other, because this is using plus and minus supplies. So, that being said, I've gotten the variable balance step done. All you do, same thing as you're aligning a scope, is you get this to move from minimum shift at 1 millivolt. However, you do need to wait for the hysteresis and the thermal effects of the transistor junctions to come out. As you can see, I'm not even touching it, and the trace is moving a little bit. The air conditioner just turned on in the lab. This is also noting in step 1 to do all of these and just make sure they can be done. If they can be done, you can skip the first 7 steps in the calibration procedure and move directly on to step 8. Now, for this particular unit, since I do know it was maintained at a large company and was probably run through a calibration lab on a few occasions and things like that, this one probably has, this one's probably going to be okay and has been adjusted recently enough where I'm not too worried about drift of components. If this had sat in a shed for a while, I'd do the whole calibration process, wouldn't even question it. But since this is since this has been done recently, I'm gonna see if we can do the abridged. If we can do the abridged, great. If not, we'll do the whole thing. This was the fixture I was waiting on. This is a 0.01% accurate precision DC voltage reference or voltage divider. So I was waiting on that guy to ship in, and we have it. We also have a precision 1% resistor as well. So next up is going to be the step attenuator balance. So what we're going to do is position this to the center line, like so. And I apologize for the long shot. I wanted to show the trace as well as the... Alright, so what we're going to do is we're going to need to move this up to 10 millivolts. There's 10. And then... we need to go to 50. It could be adjusted a little. So we're going to do step attenuator balance. Oh, that'll fit. Okay, so yeah, see now it's way off. Yep, I was doing that backwards. So it's adjusted at adjust position at 50 and align at 10. And there we go. So you adjust the positioning control with it at 50 millivolts, and then you align the step balance at 10 millivolts. And that lines up real good. Okay, so we want to go back to 10. Now we're going to adjust the 10x. A little bit of up, nope. We're into, no, it's bouncing above and below, because this will be a 1x. This will be a 1x 1 millivolt signal, so it's kind of drifting a little bit, but it's drifting above and below the center line, and it's probably just me talking on it because I'm off to the side over here, just talking on the circuit board. Like if I wave my hand near here, I can affect. This is how sensitive this is. So we're not going to mess with the 10x balance. Okay. So it wants 2 divisions below. And then this wants to be set to 1 millivolt. And now I need a 4 millivolt calibrated signal to go into this thing. So we are about to push the PG506 to its limits. Oh, it wants to use the 4 millivolt calibrator right here. No, because that's a 40 millivolt. Huh. I got a 5 millivolt. It's fine. So we got plus, and we're going to go DC. And we'll position this. And let's clean up some triggering here. High frequency reject. Okay, and our calibrator signal. Our gain is good. It's moving around a bit because of the thermals, but we have a 5 millivolt peak-to-peak signal, and we have 5 millivolts per division. So our gain is in good shape. So sensitive, that's going to come back, and that's going to be probably a fixture of this alignment procedure, is just the sensitivity. Okay, but because everything checked out and everything was good, we get to skip steps 1 through 7 And we can go right to step 8, which is checking gain, which is fine. Okay, so first things first, we're going to check drive current. And for this, I need a 50 ohm terminator. So we have a straight 50 ohm termination that goes on the plus side, which is fine. We're at 1 millivolt per division. That's in and that's in. And those are both set to ground. Give me some brightness. There we go. And then now, drive current is good. Let's check the minus. And we were at 0.1 division of deflection, so we were good for drive current. I need volts display to be 9s. Just check the preliminary procedure. Okay, quick way to set up the variable balance again, since I had to move holes in the scope. I also took the bottom of the scope off, and I took the side of the scope off. But as you can see, the air currents are much less of a problem for the plug-in. So what I'm going to do now is, with the variable balance fully counterclockwise, is where you do the position. Counterclockwise is where you adjust the control. And definitely give it some time to stabilize. It's about as good as we're going to get it. Okay, since I don't have a jack pin, I'm going to use a meter probe. But we've got 999.9 volts. And we have VC out 0 to 10. So we're going to hit positive voltage and DC here, and we are on 2 volts per division. And we have 5 divisions of deflection, 3 below to 2 above. So that gives that our comparison voltage is working correctly. All right, so we go to 1 millivolt now. Position to center line, and we're checking overdrive. So we go to VC, and now we go to ground. And yeah, that is within tolerance. But I do think I want to adjust our 167 a little bit. We'll see what that, we will see what that one does, if we can't improve that a little bit. Okay, so we got VC and then overdrive, and it comes right back and settles. So that did need to be adjusted just a little bit. All right, so we check overdrive in the opposite direction. And we need to come back just a little bit plus and minus are operating equally front and back, so we should be good there. Yeah, it does want you to iterate back and forth to make plus and minus match. Okay, I'm going to have to pause here at the moment for the calibration because I got to order a few more things. I need banana plugs to BNC short patch cords, which I don't have. So I got to order some stuff real quick from, get some stuff ordered up, and then we will continue. Okay, as I wait for the rest of the gear to finish warming up, we'll take a look at this figure right here. So this setup is a little strange. Actually, it's very strange. I didn't have any of these funky BNC to banana cables. And what's weird about this particular BNC to banana cable is it's single-ended, whereas most scope probes are dual-ended, where they have a shield and a conductor. This is calling for a single-ended BNC adapter. So I actually found these. These are unshielded BNC to banana adapters. So this will slide in here like this, and obviously you can get them in red or black, doesn't matter. I picked up the red ones. The part number on these is 3430-2. And these are Pomona connectors. So I also got a couple to keep the lead length down of short Pomona stacking patch cables, because I have come to the realization my lab was lacking in stackable BNC cables. So I will be getting a bunch of these in the near future in a couple of lengths. Stackable is just you can plug the BNC cables into each other. So the lab has not had a lot of these. I got some 12-inch ones for this particular project, but I'll be grabbing a couple of them. I'll be grabbing some more sets of these in various lengths. I have a bunch of this style of patch cable with the spring-loaded shrouds. These are nice. I'm using these for meters. These fit all of my meters, no matter what the kind of banana style is, whether they need shrouded or unshrouded. And there's been a lot of different ends for these. So I'm really a big fan of these cables. Use these a lot in the lab. I use these more often in the lab than I do actually traditional meter probes. That's probably just because of how my lab's set up, though. I'm doing a lot more alignments, things like that. But these don't stack, so that's been part of the problem here. So let me get these undone, and then we'll get this thing set up, because this setup's going to be kind of strange. Okay, when it says go after a brown and white wire, I believe this is the brown and white wire in question. So we have to disconnect this, which actually disconnects the VC output, and then we actually have to hook up the divider against to there. So I got to get a connector in there, and I've got to get something hooked up to the divider to get that working right. So let me do that, get it back in the scope, get it warming up again, and we'll go from here. This is going to be a fiddly one. Okay, I think we have this thing hooked up correctly now. So we have a 1 megohm high precision resistor loading the outputs. This one goes back into the VC input board. We have 50 millivolts square wave coming in on these two leads that are going into the top side of the divider. We have plus going here. We have ground reference into the 7A13. Now what we're going to do is we're going to set both of these to VC. Now one of the reasons that this is important is my 50 millivolts is coming in on this line on VC, so we should have a flat line with nothing. And we do. So what we need to do now is position to the center line. There we go. And then we hit DC on the plus side. Nope, I mistakenly used the calibration generator, and I have some of the settings wrong. So the calibration generator needs to be a DC calibration generator. So in my case, I'm going to use the Fluke. What is this thing? The 343A, because that'll give me the precision I need. I need to set that to 50 volts, so I'm going to do that now. Okay, so we have 50 volts as precisely as I can generate it in my lab. So what we're going to do is, for safety, we're going to turn the standard to standby. Pull this out and hook this up to the alignment fixture. So I now have my 50 volts coming in here. And let's watch the screen. All right, we'll turn the 50 volts on, which we're good. Nice and centered. Let's see, we will brighten this up a bit for the camera. And then we'll hit DC. And it is out. So this is going to need some alignment on mine, which is fine. So now we need to adjust R8G. I could live dangerously, but I think I want an insulated adjustment tool for this one. R8G is right here in this heavily shielded block for the input section, so R8G is right there. Let's check it again. VC. Now we're centered. DC. It's about 0.1 divisions, so we are good. Okay, I finally have this figured out. This is worded very confusingly in the service manual, but we've got it going. So I've got the backside of the 0 to 10 volt connector here coming out on the line, and we're coming up to this precision resistor that's going into the front side of the scope. What's on the scope screen doesn't matter, so this is all done with meter based. These two connections run up to the DM7510 using the precision sources. So what we're doing is at 0.1 volts on the volts per division knob, we're setting the comparison voltage to 4.5 volts as precisely as possible on the meter. And I'm at 4.5001 and we're kind of jumping, so back it off just a little bit. There we go. Come back a touch. All right, there we go. So now what we want to do is I need to take this and adjust this for 50 millivolt. So we're going to come down into the 1X attenuator, and we want to make sure the meter on the reading on the meter is within 50 millivolts for the 1X attenuator. So you set it on the 10X attenuator, and then we're comparing the 10X to the 1X. So I'm at 4.500, kick this down, 4.999. So we are within 50 millivolts. It's jumping around by about a millivolt. Here's what the meter looks like. And there we go. So my 1X attenuator is good. Now we need to check the 100X attenuator range. So let's figure out what we have to set up for this one now. Also, if anybody knows what the size of this jack is, I would like to get some pin probes to go in here. I think this is a 2mm banana jack, because a 4 surely won't fit. So if anybody knows what this is, let me know. I'd like to get an adapter to either go to 4mm banana or get something so I can plug some things in there, because this will be useful later with this plugin. Okay, we have the precision resistant DC resistance standard set up as before. Exactly the same way. The 1 megohm resistor is back here. I'm going to get a couple of these 1 megohm precision resistors. I'd like to not have to move this one off of here again. Also, we've moved this switch into the 100x position. It was at the 10-to-1 divider. Now it's a 100-to-1 divider. We're going to fire this up again. I need to turn the voltage standard back on. Haven't adjusted that, so it's still at 50 volts, which is fine. And operate. So, VC. We're in the center, ground and ground. We are in the center, so no movement there. I was looking for trace shift again on the line, nothing there. So the 100x DC attenuation ratio is correct. So we're good there. Okay, now we're doing the same thing again on the negative side, ground and ground. Move the patch cable down here, back to 10-to-1 on the divider. Fire this up. Give me some brightness. Center my trace. There we go. VC. Perfect. We're within 0.3 divisions, so everything is good. And now I have to do the exact same thing with the exact same thing that I did before, moving the resistor over to here. We just have to do everything we just did with the negative side. Okay, we have the similar setup, except we're on the negative side of things. Plus voltage, ground side. Set that DC. This one's a lot more sensitive. Okay, there we go. So this is what my reading is. Not that that matters for this test too much. Yep, we make spec. I went from 4.99 to 496, so we're out by about 30 millivolts. So that is good. We do not need to adjust anything there. All right, we're checking the high-frequency compensation adjustments. And I don't have the gear that's called for, so I've set up the 7A15. This is very similar to doing a high-frequency compensation in any scope plugin. It's square waves. Originally, this calls for some exotic signal sources, a Type 109, as well as a couple of charge lines and a few other things. I don't have a Type 109, and the Type 109 actually has some longevity problems and staying power. What I mean by that is the fast edges in the Type 109 were created by a mercury wetted relay, and that mercury wetted relay does not have a long operating hour time. So it only gives you about 200 hours of operation before the relays toast, and it needs to be replaced. Well, and nowadays, that's if you accidentally leave the thing on pulsing over the weekend, relays toast. Or somebody goes on vacation, relays toast. 200 hours of operation. If you leave it on 24 hours a day, that can be chewed up in about a week, which is pretty short. That's why we're going to use some different gear that does this. So there's a call out in the manual that says you need a system rise time of, actually it's right here. You need a system rise time of 3.5 nanoseconds. Well, my Type 106 can get faster than that. My PG506 can get faster than that. And at least on the positive side, I can get even faster than that with my tunnel diode pulsars. And if I had the 284 working, it would be even faster than that. So I measured the outputs of my PG506, and both the positive and the negative going pulses were in about the 800-ish picosecond range, so very serviceable for this. I have the fast rise coming through a 10x attenuator into a 50 ohm terminator, and we'll figure out what we need to do. Also, after 50 millivolts, rise time is less important, and we get into just checking for aberrations on the line. So let's just go ahead and check it real quick, and we'll see what we need. So here's our, let's see if we can focus this a little bit better. We can. Okay, so this is a nice step waveform. Let me turn on the lights so we can see the graticule. It's coming up. Let's see. We'll position the rising edge here. There we go. We're at 5 nanoseconds per division. Actually, we could spin this up a little bit more. So we're just at about 3.5 nanoseconds. So that's where we'd need to be for full bandwidth. So let's check 5, because this is now 1 nanosecond per division. So we're pushing this frame about as fast as it can go. All right, so 5 millivolts. Let me zoom in on the screen for everybody. Okay, so remember, we're at 1 nanosecond per division because we have the time base to do it. And we're looking for 3.5, so we're at 1, 2, 3. That's about 3.2, so that one's good. And where are we at? That's 2. Do I check 1? Yeah, I do check 1. Okay, so that one's okay. This is really pushing the limits of this scope, but that's fine. I'm going to judge that about right about 3 nanoseconds, so that's okay on 1. All right, so let's go to 20. Find our waveform. Stretch this out a bit. There we go. So that's about 3, so that's fine. 50. Yeah, that one's good too. All right. See, we're going down there. Yeah, that's good. 3 nanoseconds. We're still looking for 3.5, so anything above below 3.5 is good. But now we're running into a problem, because I can't put enough voltage out of the PG506. I'm topped out. Let's see if the 106 lets me run a little better. No, it's less. Interesting. So how do we get around this one? Okay, I can't check the 2 highest, or the 3 highest ranges. However, the high frequency compensation actually does not care about what the ranges are. So due to this table in 5.4, which is the high frequency adjustment, it's adjusting the connectors. It's not adjusting the... You're not adjusting each attenuator like you're doing with a scope, and the adjustments are done. The adjustments are only done with a 106 on the front end. So I can use a type 106 to hit the highest ranges, because that's what you'd actually adjust them with anyway. So the only thing that I can't do is exhaustively confirm that the highest couple of ranges Oh yeah, that sharpens it up, adding that at 50 ohm, which is fine. Stretch this out a bit. There we go. Now we got some decent. Okay, that one looks okay. And yeah, still everything's all the same. So the attenuation actually matches. Waveform looks the same. So that'll check in the plus side. I'm going to check in the minus side, which is do exactly the same thing. Just run it through the attenuator, see what it looks like. But one thing to know is on the minus side of things, you want to use a fast falling edge, not a fast rising edge. It's very easy on the PG506 to plug it into the wrong socket and get the wrong edge for the adjustment that is being done. And you can chase your tail for a couple of days if that happens. Don't ask me how I know. So let's check the frequency response of the negative connector and go from there. One other thing to note that's a little strange on these is for the frequency responses, it is from a negative volt. So for the fast rising edge, it's a negative voltage to ground. For the fast falling edge, it's a positive voltage to ground. So it starts high and falls low, or starts low and falls high. So it's backwards from what the markings are on the front of the device, which can be confusing. Make it 1 nanosecond per division because we can, and we have a fast enough plug-in. Yeah, we're still about 3 nanoseconds of rise time, so this frequency response is actually looking very well. Back this off a bit. Yep, still at 3. Oh. That's even a little bit quicker, because we're at 2.8. The increase in noise is because I moved over to the fast fall of the 106, because we're on the slowest ranges. Right about 3.5, so. All right. I could have also gotten around that way by increasing the attenuator, adding a 5x or a 2x, and getting at it that way. Let's check as high as this will let us go on the fast fall. I have to pull the 10x out. There we go. Good there. High frequency compensation on these verticals is where you can gain or lose bandwidth. So it takes some time, spend some time in this section, and in a worst case, I've had a scope, I think it was a 465 that I was working on, and the high frequency was out so much, my PG506 is topped out. So here we go. Now we can move over to the 106 and look at some. Well, you remember how I said the it was easy enough to do on the scope, where you would hit it and put the wrong plug-in in? I just did that, except I didn't set the trigger to the right side of the square wave, so we were looking at the rise on the fast fall. Which is funny, though. It still gave me 3.5, which is actually not too bad. So there's falling edge. And we'll just run down the... Now, I could edit some of these bloopers out, but some of the patrons have specifically asked me to leave them in. So we will. And I also like that, because mistakes do happen, and it's just they just do. Yep. Okay, so my high frequency compensation on this particular plugin is in good shape, and nothing needs to be adjusted. Very cool. Okay, there's been a bit of contention and discussion about these input normalizers that I'd like to go into a little bit if you've made it this far into the video. If not, I'll probably have to make another video on this, so I apologize for the repetition. I tweaked a trimmer cap on these input normalizers when I use them, just like I would do every time I use a scope probe. The purpose of these RC normalizers is to normalize the input of the device for the probes you're using. So it's a good practice to always tweak the compensate the probe for the input. The exact capacitance of the input is not as important as the attenuators matching throughout the ranges. So if you have to match the that way you don't have to recompensate the probe every time you turn the range knob. So that's really what these normalizers are doing. They're acting like a dummy probe. Now, the capacitance of the normalizer has to match the capacitance of the input. I have a couple of these. I think it's 13 through 47 picofarad. And depending on the plug-in I'm using, I have to match the normalizer to the plug-in input. But I do tweak the capacitor on the input. But then I normalize the RC dividers so I don't have to recompensate the probe every time I change the volts per division knob. If that was not done, every time you change the volts per division knob, you might have to recompensate the probe, which is not great and kind of actually a pain in the butt. So you can use a probe for this if you don't have one of these normalizers. You just hook up a correct probe, compensate it, get a BNC to probe end, and then use a actual scope probe. Don't use the long ground cable if you're going to go the probe route. Make sure you get one of these, which is a scope probe to BNC, because you don't want that ground lead flying out, hanging out in the breeze while we're working on it. So all we're going to do is very similar to a normal scope probe. We're just going to check the wave shape, make sure it works. Here's what the wave shape looks like. So we're looking for the top flat end. And then, so here we go. 10, here's 20. That looks good. 30. This also looks good. Now I'm topped out on my high amplitude, so I have to... Yep, it said I was going to need to. I have to strip out the attenuator, which is fine. And that still looks good. That still looks good. And it wants these checks to be done about 6 divisions of display. We'll bump this up. And the so this is artifacting from the signal source down here. Don't want to scratch my screen. So here is what I'm looking for. We're looking for rise, not fall. Fall's got some artifacts in it. That's just because it's the 106. And we're out. And it does say at 1 volt I need to pull the 50 ohms off because I get just 6 divisions of display, which is fine. So we back this all the way back down again. Pull the 50 ohm terminator off. Now we kick it up to the higher bands. That looks good. And this also looks very good. So, move this down, put all my attenuators back, because we have to do the exact same thing on on the negative channel. So we flip this to ground, flip this to DC, and bring this down to 10 millivolts again. Bring this down. Ooh, way too big, way too big. because we're on the negative input, everything is inverted. So my point of reference now is this part of the waveform and ignore everything else. So it's just this transition in this corner. Looks good. Looks good. Remove attenuation. Bring this way down. Bring this down a little bit. Now this is backwards from what I normally use it, because that looks good. I'm used to the amplitude going in a negative direction when I tweak the adjustment knob. So this is kind of working like standing on my head. That looks fine. That also looks good. And I'm out of gas on the 106. So we got to back it off and pull the 50 ohm terminator out. And we do this some more. That looks good. That looks good. And that also looks good. And that's my top end. So my input attenuators are well adjusted. So this unit's actually in pretty good shape. Ford took good care of it. Okay, for this plug-in specifically, we need to press into service one of my more exotic pieces of test gear. So this particular cable is used in common mode rejection ratio alignments. These two wires are length matched. Very important for CMMR because I have to have the same signal going into the two ports. So if the cable over here would say shorter, this would act like a delay line and would throw off the CMMR measurements. So this was one I had to wait for. These don't come up that often, but from some of the other vendors, you could get a T connector and then get some length matched, a pair of length matched BNC cables. This particular one was made by Tektronix. This one is matched, I think, to like 0.1 millimeters or something crazy like that. So, and this is also set as a unit. Obviously, this BNC T connector's a little strange. So that's what that's why I'm using this cable, because this, if the lengths weren't matched, this would act as delay line, and you would get signal, the same signal on both sides, but this would be offset by a offset in time, which would cause CMMR problems. So we'll get this hooked up, which is relatively easy because it's the same signal going in both sides. And now we need a medium frequency generator. So I'm going to use the SG503 for this one. It wants a 191. The 503 and the 191 are pretty much the same thing. One's a lot bigger than the others. I am not forgetting the 50 ohm terminator this time. It wants 1 megahertz. Okay, so we're going for 5 divisions of display. So we'll kick this up to 1. Give me signal. Oh, do I not have enough? Wait, no way. There's no way I don't have enough signal. I'm on the wrong input attenuator setting, I would bet. 2 volts. Oh yeah, way off. Cool. And we magically have trigger. I'm actually going to detrigger this because it's easier to get a division count on these with looking at the envelope as opposed to the individual sine wave. All right, so we have 5 divisions of signal, but the reason we have signal right now, because this is differential, is we have positive and negative, but negative set to ground, so we have nothing coming in on here. So we go to DC and we go to 1 millivolt. And now we move this down. Triggering might help this time. That pulsing that you see is actually noise in the lab. I'm still fighting with that. However, we do see we have a peak-to-peak of less than 1 division. So, and it's peak-to-peak. So it's really, actually, it's the way it's measured in the documentation is from peak-to-peak center line to top. So we're really looking at 0.4, 0.2. 1 division less display of amplitude is equivalent to a common mode rejection ratio of 10,000 to 1, which is why this cable is so important. So we're good there. Okay, so leaving the setup the same, there's a table, 5.7. And what we're going to need to do is I need to set 10 megahertz. I'm looking for less than a 1 volt amplitude at 2 millivolts per division. So let's do that. Now this is where the leveling sine wave generator comes in, because I have to bump this up to 10 megahertz and not change the level. So having this, the 191 is also a leveled sine wave generator, although they call it something slightly different. They call it a constant amplitude signal generator. It's a leveled sine wave generator. And now we need to kick this to 2. And we make it just barely. So let's check 20. Amplitude 2 divisions or less, so we make it just barely. So we got 500 to 1. 20 megahertz at 0.5. So crank this up to 20. And I should have 4 divisions or less. Oh yeah, we do. Very much so. Now, how am I going to get 20 volts peak to peak? I guess I'm going to just have to use my function generator, because it's all I got that I think goes up that high. Back this off, let my function generators warm up, and we'll keep going. Okay, warming up another signal source. I have a 20 volt peak to peak signal going into the front end at 100 kilohertz. Volts per division is 1 millivolt, and time per division is 5 microseconds. And we should have less than 1 division peak to peak of display, which we do. We can pull this back. So this has a CMMR of greater than 20,000 to 1. So that is very good. Okay, this next one's a little confusing to set up. So we move over to the 106 again, and you set VC to negative 50. Plus input is DC, minus input is VC, and this is 050.0, and then we increase the amplitude of the 106 till it comes to gradical center. So as you're setting this up, there's nothing on the nothing on the scope, nothing showing up, it's nothing, and then all of a sudden you get signal. So that's the setup for the controls, and we're still using the CMMR test cable. So then we need to do negative input mode to DC, and 0.1 volts. Two milliseconds. And this one's going to need adjustment, I think. Let me check my square wave is correct. Yeah, it is. It's right. DC, VC. I think I want a 50 ohm terminator on here. See if we can't clean up the speed of this edge. This edge might be causing me problems. Okay, so now we go to... Yeah, it's seeing the undershoot off of those tubes. So what I need to do is I need to ignore this portion and just go with this portion, because that's the waveform. Because remember, this is that undershoot off of the calibration fixture, so I'm working with this portion of the waveform and ignoring this, which is what we should be doing. I do want to adjust R28B. Well, it seems my unit doesn't have an R28B. I did find an R28G, but I just don't want to tweak that and say that's it. However, I did notice my 106 was set wrong. I had it set to 1 kilohertz, and I set it down to 100 hertz, and it cleaned it up significantly. So it's looking like it's pretty close. Very difficult to measure, but it is looking pretty good. So we'll check 10 kilohertz now and see where we go. So ground. 2 volts. Cut this in half to 25.0. 0.5. Okay, we do, this is low frequency generator again, so we move this back up to here. Actually, let me get a frequency count. We should be on 10 kilohertz, and we are. Okay. So, let's see, DC and DC, we should, there we go. Perfect. We have signal. So now we go DC and VC. So we dial this up. Gotta find it. Can't quite find it. Okay, I have to warm up yet another piece of gear that I didn't think I was going to need. I'm going to press into service the Fluke 5200A. Did not think I was going to actually need my AC calibrator for this plug-in, but this last CMMR check, it just seemed like my function generator just kind of ran out of gas, didn't have enough amplitude to feed it, which is weird. It should. So I've got the AC calibrator warming up now. Those are actually the settings that I'm going to use. I was able to dial it in real nice with the AC calibrator, but this one's been a weird one. I have not needed to press into service this variety of equipment to do a plug-in before. So these 7A13s actually they're kind of a pain in the butt. So let me let that warm up. I've got the display turned off, and then I'll do some final tweaks for amplitude, and we will just kick it and see what happens. Okay, that should be enough warm-up time. It's getting kind of toasty in the lab with all this gear on. I don't need the ultra stability of the AC reference, so we're going to just kick it in gear and see what we can do. Oh, I have to turn the AC reference on. Operate. And we have signal. Let's add a little bit more. I like that. So we ended up at 17.6 peak to peak for me. And at just checking my frequencies right. Yes, 10 kilohertz, which is well within this DC voltage references wheelhouse. All right, so what we're going to do now is we are going to kick this down to 0.1 at 0.2. 0.1. Actually, I gotta DC that. At 0.2, and we'll get some trigger. That is running a little high, about half a division, or about 0.5 divisions high. So mine does need an adjustment of C28A. But that's the lowest we're going to get. Actually, we go to 1 volt per division now. And then we also adjust C25A for lowest amplitude. That's going to be right about there. Cool. Thanks for stopping by the lab, taking a look at this 7A13 differential comparator plug-in for the 7000 series tech scopes. More is always on the way, and we will be continuing to make videos. So if there's anything you'd like to see or have any requests, leave them in the comments below, because I will see everybody in the comments, and I do read all the comments. On this one, here's our dish of shame. We have a couple of capacitors, a couple of which started leaking. Not too bad. So definitely one of the more wild plugins I've had to align. Took a lot of gear to get this done. So these are interesting to say the least. But we got through it, and everything's good to go. So, as always, more's on the way, and I will see everyone in the next video.